Alrighty, section 1.1.1. So we are now officially in unit 1. I know that's a little confusing because we just finished chapter 1, right? So technically this is our second chapter, even our third if you want to think about it. But again, we're aligning with your workbook. So this is from unit 1, right? So if you had your textbook, you wanted to consult that, it's just from unit 1. That's all it is. This is an introduction to linear and exponential equations. Now I've already seen sort of a little mini introduction about what they look like. What we're doing in this chapter is we're going to be building them. So we're going to be building them from a lot of context, a lot of word problems, a lot of situations you'd see in real life, right? Because that's the important part. It's great that we can add and subtract like terms, but at the end of the day, we need to know where these are actually useful in life. So this is a very important chapter for that. We're going to start off with interpreting structure in expressions, okay? So we're going to start off with building expressions. Remember, an expression is something that cannot be solved. Now that doesn't mean you can't build one, right? It just means stuff like 3x minus 4. It means stuff like 2x plus 5, 3 to the x, right? You don't hear me ever saying the word equals. It's equations that have equal signs. Equations can be solved. Equations have answers. Expressions just end up being mathematical statements, okay? Eventually we will start putting these together. In fact, the section after this, we will start building equations. But right now, let's just see if we can start with expressions. We'll kind of lead into it. So let's head on down. Example number 1. This is sort of a review identifying the parts of the expression. So identify each term, coefficient, constant, and factor, that we'll have to talk about, of 2 times 3 plus x times 1 minus 4x plus 5. Hint, simplify first. If you see this, in fact, you shouldn't even need to have that hint. You should always, always, always consider simplifying first, because as this is not a classic expression, right? A classic expression would be something like 3x plus 5 or 2x squared plus 4x plus 9, right? This has a whole mess of parentheses, and it has a whole mess of x's, and that's a problem. We do not want to have multiple of the same thing, because then we can't see what is actually our what is actually our term number, what is our degree, what's our highest power, you know, stuff like that. So why don't we simplify this first? We've had a whole chapter on how to do that, so this shouldn't take too long. Let's go ahead and write this over here. 2 times 3 plus x plus x times 1 minus 4x plus 5. That's our expression as it is right now, and we're going to go ahead and simplify. As we've seen before, it's always good to get rid of those parentheses first, right? So that's always sort of an indicator. Let's start with that. I'm going to start by kind of do these both at the same time. I'm going to distribute those in. So I have 2 times 3, which is 6, and plus 2x. Now I'll distribute these in. X times 1 is x. X times negative 4x is negative 4x squared. And then I'll just drag and drop that 5. So remember from product rule, if I have x times 4x, that's the 4's. I have nothing to multiply with the 4, but I've got x times x, so that's x squared. Ready? Now I can combine some like terms. I have these x's that I can combine. I have these constants that I can combine. And then I don't have anything that will combine with the x squared, right? Because x squared and x are not like terms. They have to have the same variable and the same exponent. I can multiply anything I want, but when I'm adding, they have to look the same. Otherwise, that PEMDAS gets messed up. So, looks like I have negative 4x squared plus, let's see, I have two x's and another x gives me 3 x's. And then a constant of 6 plus 5, which is 11. Now that is a nice, easy, simplified form. Oops, 11. Alrighty. Now let's start identifying those parts. So I have terms, coefficients, constants, and something we'll talk about, factors. Alright, so terms, coefficients, constants, and factors. As it was before, I might think there are like 5 or 6 terms, right? But now it's pretty easy to see that terms, there's only 3 terms. Remember, a term is separated by a plus or minus. So it's all the things that are being multiplied. So we've got negative 4x squared, 3x, and 11. Those are our 3 terms, right? And I even have a squared term, right? In my original expression, I didn't notice I had any squares. I couldn't see that. It hadn't been done yet. Now I can see I have a square term. All right, coefficients. Coefficients, remember, those are the things in front of the x, right? So in front of variables. That means we have a -4, a 3, and then remember we were debating about whether a constant can actually be a coefficient. If you want to put down 11, I wouldn't mark you off because technically you'd be right, but for this class we're just going to say they're the ones with visible variables, so -4 and 3 would be our coefficients. Awesome. And the reason I'm okay with that is because 11 is a very special kind of number. It's the constant. It's the constant, right? It's the one that doesn't have a variable on it, so it's the one that will not change when we plug in for a variable. It'll still always be adding 11, a constant 11. Alrighty, that should have all been review. If it was not, please make sure you pause and get your questions answered now. The last one we're going to talk about is factors. Factors, think about what a factor is. A factor is the breakdown of multiplication. So the factors of 6, we'll do this in like green, no, we'll do it in, having color issues. We'll do it in, I just use an orange. Really big fan of orange and purple today. We'll do it in black. So the factors of 6 would be 1 and 6 and 2 and 3, right? Those are the things that multiply together to get 6. So the factors of the terms are the things you are multiplying together. So the factors here would be -4 times x squared, 3 times x, and then 11 also has another factor. What's 11 being multiplied by? Technically x to the 0, right, or 1. So there are 6 factors for this 3-term polynomial. There always should be twice as many factors as you have terms. Alrighty, so that's just a little breakdown of all of the expression parts. So when I say things like, well, this is going to be our x term, right, so that should make sense to you. You should remember a term is going to be one of the colors, right, so a 3x, right, if this is going to be our x term, you would say it's the 3x. Or if I'm going to say we're going to come up with 5 different terms here, 2 of them are going to have coefficients, then hopefully you can remember what that means. You're going to see something with 5 different terms that only 2 have numbers in front, right? So it's important to remember that terminology, that vocab, because when we use it, we need to know what we're talking about. Alrighty, this next example is example number 2. It says Helen has purchased 3 books online from the bookstore, received a 20% discount. Shipping cost was $10 and was not discounted. Write an expression that can be used to express the total amount Helen paid for 3 books plus the shipping cost. Identify each term, coefficient, constant, factor, and expression described. This is entirely spelled out for you in this next page, so we're not going to do it together. But the expression they arrive at is 2.4x plus 10. So that's kind of the idea here. We're going to take paragraphs like this, situations, and we're going to end up with expressions like 2x plus 10. Okay? You are welcome to read this at home if for some reason excuse me, you can't access the video. Then it's in here in the notes for you. So you've got at least one broken down. If you choose not to take notes today, I really strongly advise against that. I really, really, really want you to take notes in case for some reason you can't access this video at home. Make sure that you take notes. But anyways, just one is broken down for you. That's all that's in this example. So we're just going to jump down to the next page. Steps to building an expression from context. Now here, context, that always means a word problem. Word problem. So context is a word problem. Context is a situation and some sort of event going on, right? So these are sort of your steps for a word problem. You want to read the problem and identify, maybe even underline, important information as well as the question. We saw it in a previous video that is an incredibly powerful tool. It takes huge paragraphs and makes them into nice, concise little bits of information. So make sure that that's the first thing you always do. Don't just stare at the problem and cry. The second one is defining a variable in context of the problem. So define your x, right? We always said x equals weeks or something like that, right? In our last couple problems. Or in the last chapter. We did this once. We defined x equals weeks, right? And then you can build an expression around the variable. So you can build an expression around it. And then the steps are virtually the same for an equation. You just go on to solve it. Here we will stop at building the expression. Okay. So let's take a look at what this looks like in example 3. Okay, so let's try this with example 3. A smartphone is on sale for 25% off. Andy also has a store credit for $60 that can be used after the discount is applied. What expression can be used to represent what Andy will pay for the smartphone? Identify each term, coefficient, constant, and factor of the expression described. All right. So it sounds like a situation you may have heard often. Sounds like, you know, something you might see at the mall when you go shop for a smartphone. But it seems like, so let's start with underlining. So smartphone is on sale for 25% off. All right, on sale for 25% off. So on sale for 25% off. Okay, that's the first piece of information. Andy also has a store credit of $60 that can be applied after the discount. Okay. So, write an expression that can be used to determine what Andy will pay for the smartphone. Okay. So, $60 off after discount. Okay. Now, from the expression, we're going to get our x, right? So it determines, so from, not the expression, pardon me, from the question, we're going to get our x. What expression can be used to represent what Andy will pay for the smartphone? So the expression, the whole thing, has to represent the smartphone, right? So what could x be? Well, x is probably going to be that original price of the smartphone, right? If we're dealing with original price, we're going to be taking off 25% of the original price. And then from there, we're going to be taking away another 60% of that original price, right? So x is going to be the original price of that smartphone. So let's see if we can come up with an expression around x. Let's deal with that 25% off part first. So I've got the original price, x, right? Got the original price. How does one take off 25%? Well, I definitely can't use it as a percent, right? 25% in an equation, that's not possible. So let's convert this to a decimal. 25%. Remember, that means 25 out of 100, which is going to be 0.25. 0.25. In other words, you move the decimal place over two to the left, right? Okay. So what we're going to do is we have 0.25 of this x. 0.25 of this x. 0.25. So this is how much they're going to take off. If the smartphone for some reason was only $1, they would take off 25 cents. If it was $50, then they would take off $12.25 or $12.50. Sorry. So they're going to take off 25 cents or 25% each time, whatever that price is. So x is still the price, and they're going to times that by 0.25 to find out how much we're discounting. Now, what's left over is they're not just going to let me get away with paying 25% of it, right? They want me to pay the other 75%. So they're going to take that and they're going to subtract it from the original price, right? So it's x minus 0.25x. They're going to take away that amount from the original price. In other words, I'm going to pay 75% of that x, right, of that original price. So if the original price was $100, I'm going to pay $75 after 25% off, right? We can see that works out mathematically. 1 minus 0.25 coefficients, right, subtracting those like terms, you do end up with the same thing. Alrighty. So that's the first part. So that's the information on sale for 25% off. That's the expression we can come up with. Now let's rope in that $60 credit he has, right, $60 credit. What happens if you have a store credit? Well, store credit, hopefully many of you know, is when you have money already paid to them, right? So you've either returned something or you got a gift card or something that you don't have to pay them $60. They owe you $60 in a sense. They're not going to give it to you, but they'll give it to you in the form of merchandise. So this is a free $60 he has towards this phone. So does that mean he's going to be charged $60, or are they going to actually take away $60? What do you think? Talk about it. All right, I hope you said take away $60, right? Because he wants to save money. So in this case, take away means a subtraction of $60. And we have our expression, right? So he takes away that $60. At the end of the day, whatever price that phone is, you can plug this in, find out how much Andy's going to pay, right? Alrighty, that's our expression. Alright, second part of the question says to identify terms, coefficients, constants, and factors. So let's go ahead and do that. Terms, Those are the ones separated by plus or minus, right? In this case, we've got how many? Just the 1, 2 colors. Awesome. So 0.75x and negative 60. Yes, that second term is negative 60. The subtraction comes with it, right? Because if you say it's 60, then you're telling the audience that Andy's going to pay an extra 60 bucks for some reason. Which usually you end up doing anyways, but still. Alright, coefficients. I'm just going to write these all down. Constants and factors. Coefficients are the things in front of visible variables. We only have one of those. That's 0.75, right? Constants, well, we've only got one constant term. That's negative 60. And then the factors are all the things being multiplied. 0.75 and x, negative 60, and 1. And there are our terms, coefficients, constants, and factors. Alrighty. If you have any questions, please pause the video so you can get them answered now. Otherwise, we're going to go on to example 4. Alright, example 4. Jackie is on Facebook when she sees a riddle meme. It says, the sum of 3 times the number, x, and 4 is 16. What is the number? Help Jackie impress her friends by solving the riddle. So this isn't quite an expression, but let's see if we can translate. This is more of a translate problem to kind of remind us how to do that from last time. So let's go ahead and translate this. I'm going to start underlining some stuff. Do you think it's important that Jackie saw a riddle meme on Facebook? Probably not, right? But, you know, so we probably don't need to underline that. Some people think, yes, Facebook is life, Facebook is love, but probably not important to the context of this problem. What's important over here is probably this bolded stuff. The sum of 3 times the number x and 4 is 16. And then, of course, what's important is also the question, what is the number? Okay, so we're going to need to know that. Let's see if we can break this down. Sum. Well, that's one of our 4 operations, addition, subtraction, multiplication, or division. What do you think? Which one? I hope somebody said addition. Alright, addition of 3 times a number x and 4 is always the equal sign, 16. So the sum of this and that, we can rewrite as 3x plus 4 is equal to 16. And that's how we'd convert it. Right? So we convert it. Then we can go ahead and solve it. Subtract 4 to both sides. End up with 3x equals 12. Or divide by 3, x equals 4. Which is all fine and dandy. So the number is 4. Now, because we actually found an answer, that must have been an equation, right? So an equation has an equal sign. This is not an expression, but still important to be able to translate that stuff, right? Being able to translate things like the sum of a number, 3 times a number, and 4 is 16. Being able to translate that into something you can actually use. And now Jackie can go impress her friends. The number is 4. Haha, she's so smart. Alrighty, let's head over to example 5 now. Tara and 2 friends had dinner at a Spanish tapas restaurant. Spanish tapas are just tiny plates. Think of it like an appetizer restaurant. That charged $6 per tapas. The 3 of them shared several tapas. The total bill included the tax of $4.32. Write an expression to represent the scenario. Identify terms, factors, constants, and coefficients that represent the number of tapas tapas ordered including taxes. Okay, I'm actually going to let you guys try this out to begin with because it's very similar to our first problem. So our third problem, sorry, the one we did up here with the price. So I'm going to let you guys try this out, and then when you finished it, we'll reconvene and we'll do it together. So go ahead and pause the video now, get your questions answered at the same time. Alrighty, I hope you tried this out yourself. Let's try this together now. So I'll start by underlining. Tara and her 2 friends had dinner at a Spanish tapas place. Well, that's awesome. That's not really important. What is important is that they charge $6 per tapas. And yes, it's per tapas. Tapas is... Anyways. The 3 of them shared several tapas. Several. That sounds important. It's not actually a number, but it could be an important word. The total bill included taxes of $432. And they want me to write an expression to represent the scenario. And then they want me to do the stuff on the bottom here. Okay, so let's start with writing down important information. They charge $6 per tapas. There were several. And then the total bill also had taxes of $4.32. Okay, so from this information, I can tell that this is probably going to be our X. Keywords like that, those generic, several, a bunch, a few, things like that, those usually translate to your X. Now, they also come out of the question, right? The question is to write an expression, so the expression is going to be our answer. But we still also need to define an X. So I'm going to define this as the X. This is going to be X number of tapas that they eat. X will be how many tapas. If they ate 3 tapas, I'll be able to plug in 3. If they ate 10 tapas, I'll be able to plug in 10, right? So that's how I can find, or that's what I'm going to define my X to be. Because of that, the total price of the tapas is going to be however many they ordered times the $6 per tapas, right? So if they ate 2 tapas, they'd pay $12. If they ate 3 tapas, they'd pay $18, right? So I can use little numbers to kind of see what's going on, and then I can I can plug in for X. So if they eat X tapas, it's going to be X times 60, or X times 6, pardon me, $60 tapas, that's expensive. So $6 per however many they ate, right? Per however many they ate, it tells me it's 6 times X, because X is the number they ate. And then I can tack on the tax, right? The tax is already included in the bill. Usually tax does, depend on your original price, but here it tells us that the total bill just included this tax of $32.40 or $4.32, right? So that's just included on the end. That's just the tax. And I have my expression. 6x plus 4 times 3.2 plus 4.32. Awesome. Last thing they wanted me to do is identify terms, coefficients, constants, and factors. So T, COE, con, and fact. Okay, terms, right? Anything separated by plus or minus, so 6x and 4.32. Coefficients, any visible coefficients, we got 6. Constant is the one that is unaffected, right? And the factors are 6, comma, x, whoops, comma, not point, and then 4.32, comma, 1. So 6 times x and 4.32 times nothing. Well, times 1. Alrighty. Hopefully this is starting to catch on a little bit. Notice the underlining saves you a lot of time. Some things defining your x, right? Saves you a lot of time. Let's do one more. And this time, let's see if we can build an exponential. So let's do example 6. At the beginning of the school year, Javier deposited $750 into an account that pays 3% of his initial deposit each year. He left the money in the bank for 5 years. Write an expression to represent this scenario. Identify the terms, factors, and constants. How much interest did Javier earn in 5 years? After 5 years, what is the total amount of money Javier has? Okay, so let's start. That's a lot of information, right? That's quite a big paragraph. So let's start with underlining. Underlining. At the beginning of the school year, probably not that important, right? Probably not that important. Javier deposited $750. That sounds important. That sounds pretty important. In an account that pays 3% of his initial pays 3% each year. Those all look pretty important to me. He left the money in the bank for 5 years, and then they want us to write an expression that represents a scenario. Okay, so we'll underline, write an expression. Alright, so he starts with 750. Starts with 750, right? That's what deposited means. He takes $750, he puts it into the bank. So that's what it starts with. And it pays 3% a year. and he leaves it in there for 5 years. All right, cool. And then they want to know how much after the 5 years. Oops. Okay. Now we've talked about this once before, but let's remind ourselves. An exponential equation we saw in our introduction to, our introduction worksheet, they look something like this. They look something like that, right? Now here they've asked us for an equation, so we're not going to really focus on the an expression. We're not going to really focus on the y part. So the equal part just goes away. So this is our expression. It's going to end up looking like this. Now it's important to remember what these different parts are. So again, we'll talk about this a lot in 1.2.2. Sorry, 1.2.3. But here, let's just go a brief overview. So A is always going to be your initial amount. Initial amount. Remember, if you remember from our singing contestants problem, right? That was the original number of contestants, the 64. B is going to be your rate. We cut half of them each time. A rate. Oh, that's a horrible rate. Hold on, let me rewrite that. Rate. And then X is going to be the time, right? How many weeks was the singing competition running, right? And then we ended up with one person winning the contest. So that's kind of how this breakdown works, and that's usually always how it breaks down, okay? You might see a few altered forms. You might see some different things happening based off the situation, but this is the essential breakdown. A is your starting value, your 64 contestants. B is your cuts them in half, your rate. X is going to be your time. Okay, so how many weeks was it running? Same situation going on here. So let's see if we can start plugging in some stuff. Let's see. What does this part sound like? Starts with $750. Does that sound like an initial amount, a rate, or a time? That sounds like an initial amount, right? An amount, 750, starts with initial, right? So our initial amount, we are not going to use this color because it's horrible. Let's use a darker green. 750. That's our initial amount. Okay? That's our initial amount. We'll come back to the rate for just a sec, but the years, that sounds like a time, right? So the years is actually, well, for now, let's just call the years X, because we still need an X in there, right? We need an X. 5 years kind of helps us answer the question. Now about that rate, it says it pays 3% each year, right? So that, in other words, an additional 3% each year. So are they really just giving me back 3%? We really have three choices here. Either they're taking 3% from my account, meaning it's going down 3%. They're paying me only 3%, right? So they only give me back 3%. Or they give me all of it back and 3% more. Which one do you think it is? It's actually the third one. They're paying me everything back, right? Because you don't want to use a bank that takes your money. You want to use a bank that pays you more, right? So they give me the whole $750 back, 100%, and 3 more. So what this actually translates to is 103% each year. 103%, right? That's how a bank works. You wouldn't want a bank that only gives you back 3%. That's like, let's see, 750 times 3%. That's $22. They took your $750 and they're now only giving you back $22. Yeah, that would be a horrible bank. You really don't want to use that one. Instead, you want to use a bank that will keep your $750 for you and then also pay you 3% more, right? So our rate is actually 103%. Those of you who have bank accounts, very important to remember that, okay? If you're going to get one, eventually all of you will. Very important to remember that you want things that pay 3%, right? If you have to pay them, you want small numbers, right? If you want them to pay you, you want big numbers. So that's kind of what's going on with our rate here, which means when we plug in our rate, obviously, again, just like in the last couple problems, we don't want to do it as a percent. That sounds weird. So we'll change this into a decimal, 2 places over. 1.03. Our rate's going to be 1.03. So 103%. And we have our expression. We have an initial amount, a rate, and a time. Okay, so we have the expression. Check on the first part. Now they want us to use it. Let's answer the second question. How much interest... Okay, how much interest does Javier earn in 5 years? How much interest? So let's actually do the second question first because it's going to come straight out of our expression. We'll do the first one in just a sec, I promise. So after 5 years, what is the total amount of money Javier has? That comes straight out of our expression. Here we want to know after 5 years, X is our time, So let's rewrite our expression down here. 750 times 1.03 to the 5 years is going to be 750 times 1.03 to the 5th is $869, and it says you can't see it on my calculator right now, but if you're doing it with me, 4.55555555557. So I'm going to round that, since it's dollars, to 4.6. Oh, sorry, 0.46. That's how much he'll earn after 5 years. Awesome. So notice my expression just gave me how much he's going to earn after 5 years. I didn't have to sit here and go, okay, the first year he earns this much, the second year he earns that much, the third year. So that's the point of these, right? It's to save you a lot of time. Imagine if he had left it in there for 25 years. Do you really want to be sitting there adding 1.03 for 25 times? No, you want to just be able to plug 25 in and move on with your life. So that's how these exponential expressions become very handy, especially when you plug into them. But let's see how much interest he earns. Now that's an important word that some of you may not know yet. Interest. Interest is the actual money the bank is paying. So it doesn't include that $750 he starts with. How could we find the interest, just the money that the bank is paying? What could we do? Think about it for a sec. Right, we could take it away, right? So the money the bank is paying, this is the total he has. Take away the $750 will give you how much he has in interest. So let's go ahead and do that. The $869.46 minus what he pays, right? So what he put in the bank, that's not really what he cares about, minus the $750. The bank's going to pay him $119.46. That is a pretty good bank. For 5 years, paying them over $100, that's pretty good. It's pretty good. It's pretty average, too. It's what you'll see. So maybe when you're choosing bank accounts, it's important to remember things like that. How much interest am I going to earn on this stuff if I leave it in there? It could be a lot of money, right? Alrighty. So that's pretty much how you break down an exponential expression. We've talked about a lot today. We've talked about exponentials. We've talked about setting up linears, but mainly we've been talking about expressions, and expressions are different than equations, right? These ones you can't actually solve until they tell you to plug in a number. This one, it's still an expression, definitely still an expression, right? No equal sign. But once they tell us what we can plug in, we can simplify, right? We simplified it down to one number, right? So you can simplify that down. If they don't tell you what to plug in, though, you can't plug in what you want. Sorry, you can't set it equal all of a sudden. In the next couple sections, we'll be doing equations where we set it equal to y, and then we'll actually find a lot more answers. But remember, these are the most important things, the steps to building an expression or an equation: reading, underlining, what's important, then try to build your equation. If you try to build your equation or your expression from the get-go, you're always going to be confused. It's always going to hurt, it's always going to be painful. But if you take the second to underline, you'll be fine. You'll be fine. Alrighty, so that's it for today. Go ahead and ask any questions you have. Otherwise, you may start your homework, and I will see you next time.